and then some new stuff after. But we're going to start with these sums, and it's basically all just understanding what does this notation mean. This crazy big capital letter S for sum in Greek, what does it mean? What do you do with all these i's? You have to figure out what they mean. Aside from understanding the notation, this is a question that you might see in like a 4th grade classroom. So once you unpackage the question, the actual question is super simple. It's just understanding what it means in the first one and the second one. So let's do that. Let's see what people said. Let me raise this up a little bit. Okay, so we're going to start with this one. Last chance to change your answer. What did people say? People said 2i plus 3. Okay, 0 and 1 were popular. Those are not right. Last class, 5 was popular. Let me see if 5 was popular this class. Yeah, 5 is really popular. 5 is a reasonable answer to think. It is the wrong answer, but it has something to do with the question. So if you said 5, I'm still proud of you. If you said 1, then I think you were just trying to save time. Let's see, why is the answer 5? Why is that a reasonable answer? And I have to bring this window over here. Why is the answer 5 reasonable? Let me open a window. Stand by. Oh boy. Now nothing works. Okay, we'll try again. We'll click on this, and we'll go back to this, and then we'll go this. Okay, this is what we want. This is what we were doing last class. Okay, great. Series, and we did some series, and we wanted to get to today's class is on not algebra, series, properties of series. Today we're doing these arithmetic series and geometric series, of which the 2 questions were an example. This is on page 337 if you want to start flipping. So the question that we're warming up with is not in the notes anywhere, but is a good warm-up question. I equals 1 to 3, and it was 2i plus 3. And what you got to do this sum is just figure out what the terms are. And there are 3 terms. So the I values go from 1 to 3. So you're going to have 3 terms. You're going to have I equals 1, I equals 2, and I equals 3. And you've got to add them together. So that is what the sum means. This big, crazy, scary Greek thing just means add them together. Okay? And when you add them together, you got to know what they are. The first one, when I equals 1, is 2 times 1 plus 3. I just plugged in I equals 1. I was 1, and I plugged in I equals 1. 2 times 1 plus 3. And 2 times 1 plus 3, as you probably know, is 5. So if you said 5, you told me the first term in the sum. 2 times I plus 3 is 5 when I equals 1. That's the first term. But I want the whole sum. So this whole thing means add them all up. I don't want just 5. I want 5 plus the next number plus the next number. What are the numbers? The next number is going to be 2 times 2 plus 3. 2 times 2 plus 3, which is also known as 7. 2 times 2 is 4 plus 3 is 7. Or you could say we went up by 2 from 5, right? So this factor of 2 means every time you add 1 to I, you go up by 2. Multiplying I by 2 means you add 2 every time. So 5 plus 2 is 7. And if you follow the pattern, 7 plus 2 again will be 9. And 9 is 2 times 3 plus 3 is 9. So the real question is actually what is 5 plus 7 plus 9, which is something you might see in an elementary school class. And if you add this together, 5 plus 7 is 12, plus another 9 is 21. So it's 21. I'm going to write 21 over here, and I'm going to leave a little line. I'll fill in a second. So the correct answer is actually 21, not 5. But 5 is, on the right track because it was the first number. So how many people? So 30 people said 5, which was almost half the people. Did a lot of people get 21? Yeah, well, 10 people got 21. Okay, so not very many. Most people picked 5. And 5 is the first number, but I want the whole sum, which is 21. So I'm still happy with this because lots of people got the right thing. Let me think. I'm trying to think of how you would get 9 or 15. I guess 9 was the last number. It's 5 plus 7 plus 9. 15 is the sum of the first 2, right? 5 plus 7. No, 5 plus 7 is not 15. I don't know how you get 15. If you're one of the 7 people who got 15 and you want to tell me, oh, I got it like this, tell me now. Or is there anything else I can clear up about this one? This one should be pretty straightforward, unpackaging the notation. Maybe some people missed the class it occurs to me, a lot of people maybe missed the class on Friday from the snowstorm. So there is the video you should watch of the other class. Maybe that's why a lot of people thought it was 5. It's not 5, it's 21. So the 21 is correct. Questions or comments about this one? Maybe I'll give you a chance. Put your hand up if you haven't seen the class from Friday yet. Okay, lots of people. So if you haven't seen the class from Friday yet, you got to pass. That's totally fine. Now it occurs to me why this was harder than I thought. You've never seen this notation before. We did it on Friday's class, which was recorded for you. Okay. Okay, so that's what the notation means. Maybe it makes sense now. Otherwise, you're going to have to go back and watch the video. Let's do the next one. The next one is harder. It starts at I equals 0. Let's do the next one. So the next one is I equals 0. That's the sum from I equals 0 to 2 of 1 over 5 to the power I. And again, we're adding things up. That's what this means. Let me try to make my color scheme the same. So this crazy big S. In a lot of movies and stuff, they use these big letter S's to mean E. So they'll say like, you know, you're like, there's some movie set at a frat house, and they'll write this, right? Greek. That's not Greek. That says grsk. Okay, so this is the letter S. So never mix them up. This is all wrong. Okay, so the big letter S, what does the big letter S mean? S means sum. So we're adding up things. There's going to be 3 things in this one. The big letter S means add things up. And we're starting here. We're not starting at 1. We're starting at 0. So I equals 0 to 2. So the first thing is I equals 0. The next thing is I equals 1. And the next thing is I equals 2. Those are the 3 things we're doing. And now we got to plug in the I into the formula. So when I equals 0, it's 1 over 5 to the power 0. Right? So when I equals 0, you get 5 to the power 0. When I equals 1, it's 5 to the power 1. And when I equals 2, it's 5 to the power 2. So it's 1 over 5 to the 0 plus 1 over 5 to the 1 plus 1 over 5 squared. Those are some fractions. You know, 1 over 5 to the 0. You got to figure out what that is and plug them in. Let's see what people got. What did people say? Okay. Lots of numbers, 0 and 1. 1 is a good hint to me that people are trying to do it quickly. But in this case, 1 is actually the first number. So the first number is 1. And that's because anything to the power 0 is 1. So that's 1 divided by 1, which is 1. So the first number is 1. So there's more, but the first number is going to be 1. So the first number is 1. So that was good. So same thing as before. Lots of people got this one. What else could you get? 0. 0 is not right. So I equals 0. But 1 over 5 to the power 0 is something else. So the things you add up, you got to apply the formula that you see. So even though I equals 0, the term you're adding up is not 0. It's not 0. Okay, lots of numbers like 2, 3, 4, 5, 6. 0.2. 0.2 is also a very good guess because when I equals 1, you get 1 over 5. 5 to the power 1 is 5. 1 over 5, also known as 0.2. 0.2. Okay, last but not least, you have to add up this term, and this term is 1 over 25. 1 over 25. What is 1 over 25? It's 0.04. Okay, so 0.04, if you add them all together, you should get 1.24. Let's see, did anybody get 1.24? I have to scroll down a little bit. 1.248. That's very close. 1.248. I guess if you added up an extra term, if you kept going, if you didn't stop, and you did, so this is wrong, don't do this, but if you did 1 over 5 cubed, 1 over 5 cubed is 0.008, right? You would get the next term, and the next term, then it would be, if you had it going from I equals 1 to 3, from 0 to 3, then you would have 1.248, but it's not. The correct answer is 1.24, which 4 people got. So congratulations to those 4 people. 4 people got it right. Let's see. Yeah, 5% of the class, 4 people got it right, which is maybe not surprising if a lot of people didn't see the video on Friday. All right, any questions or comments about that one? Maybe even if you didn't see the video, you're starting to understand the pattern of adding up and what it means. Okay. So even if you haven't seen the video from Friday's class, you should have by now seen the video from 3 Fridays ago. 3 Fridays ago was the Friday right before reading week, and we did something very similar right before reading week. We did geometric and arithmetic sequences and their sums. And actually, the 2 examples I gave, aside from this crazy notation, are things you've seen before. This sum, 5 plus 7 plus 9, is very similar to one of the questions that's due on the homework today, where you have a list of numbers and it says, please add them up. It's going up by 2. This is the sum of an arithmetic sequence. And there was a formula in the videos for the sum of an arithmetic sequence. The formula is the number of terms times the average of the first and last term. First and last. So you could add it up the normal way, or you could add it up the way that if you're excited about arithmetic sequences like I was when I was in 3rd grade, you add it up like this. So you take the average of the first and last term, that's 5 plus 9 divided by 2. You take the number of terms, that's 3. What's 3 times 5 plus 9 divided by 2? Well, 5 plus 9 divided by 2, the average of the first and the last term is actually, in this case, the middle term. So this is 3 times 7. Right? There's 3 terms. The average value is 7. So what is the sum? It's 3 times 7, 21. So look, we did the whole thing. Instead of adding up 3 numbers, you can do 1 multiplication, which seems stupid when there's only 3 numbers. But if you have 1,000 numbers, it saves you a lot of time. And that was what we talked about in the video 3 weeks ago. We're going to go over it in the notes now, but quickly, because we've already done it. That was the sum of an arithmetic sequence. So that's what we're going to do, and that's what we did before. What about this thing, the sum of 1 over 5 to the I? Well, earlier, last class, we talked about these limits. And it turns out that if you do this sum, 1 plus a fifth plus 1 over 25 plus 1 over 125 plus dot, 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 and this is the sequence 1 over 5 to the power I, this is exactly one of those Mr. Beast things, right? Mr. Beast is trying to give us $1, but he gives us $1, and then he has to pay the tax, which is a fifth in this case, and then he has to pay tax on the tax, and so on and so on. And we saw, how do you do this? Well, the answer is just give me $1 and then give me enough money to pay for the tax. You do 1 minus 1/5. And that dividing is exactly the right solving. So solve for x. Solve for x. X times 1 minus 1/5 equals $1. So if Mr. Beast wants to give me $1, instead of doing this whole thing of giving me infinitely many rounds of paying for the tax, he can just solve for x, and he can solve for x with x is such that x minus the tax equals $1. And if you solve, you get 1 divided by 1 minus 1/5, which turns out to be 1 over 4/5, which is 5/4, also known as 1.25. So if you were to add up the sequence forever, you would get 1.25. That's if you add up infinitely many things in that sequence, it's 1.25. The sum of the first 3 terms, 1 plus 0.2 plus 0.04, is 1.24, right? The infinitely many terms that come afterwards only do 1/100th. They give you one little pip. From 1.24 to 1.25 is the infinitely many terms that come here. So all of these things add up to 1 over 100. So we're going to see that in a second too. So we haven't sort of formally done these infinite sequences yet. They're going to be coming up in a second. But again, the sum of these geometric sequences, we saw the formula 3 weeks ago in that video from right before reading week. So that's a kind of a little preview of the first half of the class. And we're going to go, sort of quickly because we've already done a lot of it. And I think you see the big picture here. We're trying to find these formulas for sums that look like these things. Any questions or comments about that before I move on to the notes? And we're going to do the same formulas again in the notes. But I did find that this section was very wordy, and there were a lot of formulas and symbols. So it's easy to get lost as to what's going on, which is why I wanted to start with this kind of big picture. What are we doing? We're adding up things that look like this. Okay, let's actually do it in the notes then. So in the notes, I got to click here. I click here. Okay. Okay. Here is adding up an arithmetic sequence. And adding things up is called a series. So adding up an arithmetic sequence is called an arithmetic series. So a series means adding up. Adding up. This is on page 337, if you're trying to get to where we are. And what does it mean to add it up? This is the formula for an arithmetic sequence. This is the formula for the sequence. Arithmetic sequence. Right? The ith term, sequence. Okay. The ith term is a plus I minus 1 times d. Every time you go up, you add d, you start at a. So it's the sequence that starts at a, then it's a plus d, then it's a plus 2d, so on, all the way up to a plus n minus 1 times d. That's what we're adding up. And in the notes, they tell you, they say, When you add it up, you get this formula. And here's what they wrote. Here's the formula you get, they say. The sum equals, and then there's this big formula. And there is an n over 2, and then there's some other thing. I prefer to write it like this, which is, of course, mathematically the same. N times a plus n minus 1 times d divided by 2. So that's the same exact formula written slightly differently. And now you can see the parts that I was talking about, which is the number of terms. This is the number of terms. And you can see the other two things. This is the first term. This thing is the last term. And by adding them in together and dividing by 2, this whole thing is the average of the first and last term. So that's a nice formula. The number of terms times the average of the first and last term. Okay. And then in the notes, they have a couple little things. Okay, one is the thing I just said, right? The first and last. So if you don't want to copy down my scribbles, you can just read this bullet point. It's the average of the first and last term. The other thing they say is that this is a famous formula, well-known. This is a well-known formula. And it's, if you want to sum up 1 plus 2 plus 3 all the way up to n, the formula is n times n plus 1 divided by 2. This is the formula that little baby Gauss knew, and it threw off his teacher who was trying to make him spend all day adding numbers. Gauss just did this formula with n equals, I think, 1,000 in the video. So the sum of 1 plus 2 plus 3 plus ... plus 1,000 is equal to 500,500. That was what we did in the video. N times n plus 1 divided by 2. That's the statement of the formula. Then on the next page, this is my favorite part so far of the notes. This is the usual derivation you probably saw in high school. Put your hand up if you saw this in high school. You saw how to do the sum, how to get the formula in high school. A couple people, three, 4 people. Put your hand up if you did not see it in high school. Okay, more people. This is what I was expecting. So let's correct the notes you probably didn't see in high school. But you did see it in the video, in video before reading week. So okay. So we didn't see it in high school, but we did see it in the video before reading week. Yeah. So I won't go over it again here, but it is this trick of you take the sum, you flip it backwards, and then you have these columns where the sum of each column is the same thing, and that is how we add it up to get this. So it's a really nice trick. It's one of my favorite tricks in all of math. I just think it's so nice that you can take something that looks like it's impossible to do and turn it into one multiplication. Like, nothing is nicer than that. Something that looks impossible becoming possible. Yeah? No. So maybe a bonus question would be, but there's no good way to ask you, do you know how to prove something within the scope of the things we're doing in this course? So there might be a question where you have to use this formula. There might be a bonus question, something like this. But if you just ignore the video and you only learn the formula, then you will get by just fine. Yeah, that's a good question. Okay. Yeah, these kinds of like fun proofs, I'm showing them to you because it's like if we walked by, we're in a museum and we have to get to the end of the museum and we walk by the Mona Lisa. I'm going to stop and show you the Mona Lisa, even though strictly speaking, we can walk by it. Okay. Other questions or comments? Okay, so since some people haven't seen this notation before, I think this is a good one. Let's stop for a minute and you guys try to do this one. Try to do this sum. The sum from I equals 10 to 20 of I. And what is it? So take a minute and try. I will start a timer. And I'll give you 2 minutes. Okay, look, I even made it a problem in Mathematize. Now you can enter in your answer. So enter in your guess. Again, it's okay if you get it wrong, but I want you to try to do it. Okay, I added on another minute, but now there's like 30 seconds left. So think about wrapping it up. Can you get to the answer? Can you figure out what it means and what the answer is? Okay, let's look at what people said. I'm very curious. Okay, numbers. So again, 10 is a good guess because the first number is 10. When I equals 10, the formula is is 10. 20, does it say negative one person picked 20? That's exciting. Okay. Is there like a ghost in the room? Okay. Some people said 200. Some people said 165. It's one of those. It's one of those. Yeah, okay, so it's 200 versus 165. And there's a common mistake some people make here. Let's go over it. So hopefully you at least figured out that this is the sum. By the way, maybe I'll say this before I do the problem. This is a great question for the midterm because it's super easy to write down. If you know what you're doing, it's like a snap. It really, like if you studied, this is an easy question. If you haven't studied, this question is impossible. That's why this question is so good for things like the midterm. But how are we going to do this question? First, let's figure out what it says. So this is a sum. So what is this thing? It's some big sum. We got to add up the numbers. I is 10, then I is 11, and we go all the way up to I equals 20. That's what the top and the bottom mean, right? I equals 10 to 20. And what are the terms? What are we adding up? Whatever the formula says here. And the formula says I, so it's just I. This is 10 plus 11, all the way up to 20. So it's the sum of the numbers, 10 plus 11 plus dot, 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 all the way up to plus 20. That's what we got to figure out. Again, if you want to use my favorite formula, you would do the number of terms times 10 plus 20 divided by 2, the average of the first and the last term. How many terms are there? This is where you can make a mistake. This is where you can make a mistake. A lot of people say the number of terms, we're going from 10 to 20. How many terms are there? 20 minus 10. 20 minus 10, right? We started at 10, we ended at 20. You subtract them, that's how many there are. That's wrong. The answer is 20 minus 10, and this is a really important thing, plus 1. Plus 1. Don't forget. Don't forget. Okay? And the way to remember this is, suppose you're like a little kid and you're counting 1, 2, 3, okay? How many things do you have if they were 1, 2, 3? If you do 3 minus 1, that's 2. You think you have 2 things, right? If you have 1, 2, 3, that's 3 things. It should be 3 minus 1 plus 1. 3 minus 1 plus 1 equals 3 things. Another example, I guess if you do 10, 11, 12, right? If you do 12 minus 10, that would say 2, but you got to add on the plus 1. Don't forget the plus 1. Plus 1 equals 3 things. Okay, so this formula, if you have listed things and you want to count them, you got to do this plus 1. Don't forget the plus 1. So in our case, this is 11 things. 11 things. So the actual final answer is 11 times 10 plus 20 divided by 2. The average of 10 and 11 is 15. So 11 times 15. And the trick for multiplying by 11 is you do 150 and then 15, right? And then you smoosh them together, so you get 165, right? 15 with the sum of 1 and 5 in the middle. So if you said 165, you got it right. Very good job. I didn't have time, and I didn't want to show the right answer here, so I can't hit submit correct answer, but believe me, the right answer is 165. If you said 200, then you were off by a little bit. Actually, okay. I thought a big mistake would be being off by 1. I thought this would be the mistake, which I guess would give you 150. If you said 150, you forgot to add 1. Only 3 people did that. Okay. Lots of people went the other way to get 200. I don't know how you get 200 here. Maybe there's some other simple mistake you can make. Okay. Okay. All right. Maybe you could, if to do 200, you do. I don't know how you get 200. I'm going to give up. Okay. Any questions or comments about that one? That's a good example of a midterm type question that combines sort of all the stuff from this part on series. Okay. So that's it for arithmetic sequences. Next up, we have geometric series. Geometric series. And in geometric series, instead of adding d every time to get a to a plus d to a plus 2d, we are multiplying by r. So the sequence is r, like a pirate, exactly. A times r squared. Oh, okay, hold on. You only multiply each term by r, so you've done 2 multiplications by r, ar squared, and you're going all the way to the nth term. And we're going to skip ahead a little bit here. There's an example here. I'll make this extra. These are 2 problems we've already done before. We already know the answers to a and b. We're just writing it in new notation. But we're going to skip all the way to this nice formula, which was the sum of a finite geometric series. This formula was in the video. Formula in video. Formula in video. Okay. So this is the formula. And how did we get this formula? It was, again, the thing you probably didn't see in high school. You didn't see in high school. Which is you take the sequence, you shift it over by 1 by multiplying by r, and then you do this cool subtraction. So in the video, we took these 2 equations, we subtracted them together, and there was all these terms canceled out. This term canceled out with that term. It was this big, exciting thing. Again, something that looks really hard, but if you think about it in the right way, it becomes simple. That is the beauty of math. And we got this nice formula for Sn, which if you rearrange becomes this formula. Okay, is it on the next page? Yeah, Sn equals a times 1 minus r to the n divided by 1 minus r. That is the formula for a finite sum. And finite means we're adding up the first n terms. So you see there's a big n over here. Oh, sorry about that. Okay, so Sn involves 1 minus r to the n. What happens when n goes to infinity? If n goes to infinity, you're adding up more and more terms. What happens if you add up infinitely many terms? Well, you just have to do the limit as n goes to infinity of r to the n. And the limit as n goes to infinity of r to the n is something we did before. This was the limit of a geometric sequence. This limit is 0 when the absolute value of r is less than 1. So for numbers like 0.1, 0.5, 1 over 5 was the example we started the class with. In Mr. Beast's example, it was 10%, 0.1. In a sequence, as long as the common ratio is less than 1, it can be positive or negative, as long as the size of the number is less than 1, then this limit, this thing in pink, will become 0. And when this thing in pink becomes 0, you get this formula. So you have the sequence a times 1 minus, and then over here, r to the n divided by 1 minus r. If the thing in pink goes to 0, this goes to 0, then you are left with this nice formula, a divided by 1 minus r. And that's the formula for a geometric series with infinitely many terms. Here is, let me put this one up so you can do it. I'm going to do one example in a second. So this is explaining why, this limit. We're just going to go straight to the example. So I'm going to do the example in 1 second. But this is a good time, questions, comments about this one? Yeah. That's a great question. If the value of r is greater than 1, that's a very good point to make. So it's not written here. This result 39 says r less than 1. Oh, okay, here it is. Here it is. When r is greater than 1, the series is divergent. That's a polite way of saying the limit does not exist, right? And the reason the limit does not exist is we have 1 minus r to the n, a times 1 minus r to the n divided by 1 minus r. And in that situation, the r to the n explodes, it diverges, and everything else is just constant, so the whole thing diverges. So yeah, very good question. If r is not less than 1, and it's not shrinking down to 0, then the whole thing blows up. It either goes to infinity, or it does this like plus infinity minus infinity thing. In either case, it diverges. Does not exist. Yeah, okay, good. Thank you for noticing that. Great question. Any other questions or comments? Okay. So we're going to go on to this example. This example is asking you, please do this infinite sum. And the only way you can do an infinite sum like this is you have to recognize the formula. So this is a geometric series. The first term is a equals 5, and I see that from looking at the first term. The first term is a equals 5. What is the common ratio? What do you have to multiply 5 by to make negative 10 thirds? So r is the common ratio. It's going to be negative 10 thirds divided by 5, right? The thing you have to multiply 5 by to get negative 10 thirds is negative 10 thirds divided by 5. That's how multiplication works. So r is negative 10 thirds divided by 3. Okay, and that's negative 2 thirds. So r is negative 2 thirds, which I got by looking at both of these things and dividing. So r I got by looking at both of these and dividing them, because to get from one to the next one, it's r. You could have also done, you could have done these two. That would have worked too. The ratio of negative 40 over 27 divided by 20 over 9 is also negative 2 thirds. It's always negative 2 thirds. Okay, but now you have the two things. So what is the sum? It's very simple once you know the ingredients. The sum by the formula is a divided by 1 minus r. In our case, it's 5. Sorry about that. 5 divided by 1 minus negative 2 thirds. Okay? And what is 1 minus negative 2 thirds? That's 5 thirds. So 5 divided by 5 thirds, also known as 3. So this sum is 3. Okay, why is the sum 3? It kind of makes sense. You started at 5, then you subtracted a bit. You subtracted a little bit more than 3, right? Negative 10 thirds is subtracting 3 and a bit. So now you're at like 2, then you added some back on, then you subtracted some. So you're going back and forth and back and forth. On a number line, it would look like this. 5 minus 10 thirds, and then you would do plus 20 over 9. And what the result is telling you is that you settle down, after this plus minus stuff, you settle down exactly at 3. 3 is the limit. Okay. So as an example, quick plugging in of the numbers. Questions or comments about that one? So I think that will be the last example of chapter 8. We're going to start chapter 9. This example I will leave as extra, which is, again, very similar idea. Identify A and R. And we're going to move on to chapter 9. Some people like chapter 9. Some people don't like chapter 9. Chapter 9 is a bit different because it is more real-life applications. So it's some applications in finance. And so some of it is going to be like definitions and like real-life things people use. And it's also going to bring us to this idea of compound interest, which is interesting. So we're going to get to interest. We're going to start with simple interest. Simple interest is in the name. It tells you what it is. It is simple. And it's so simple, you just need one formula. Here is the formula for simple interest, which says that the amount of interest you get is the principal times the rate times the time. The principal is the amount of money that you started with. So imagine you go to a bank, you deposit some amount of money. That amount of money is your principal. You leave it in the bank for some amount of time. That's the time. And the bank has an interest rate. So this rate, maybe more accurately, is the interest rate. That is how much money they give you in interest per unit time. And if you multiply these three things together, it will tell you how much interest your money earned while it was sitting in the bank. That is I, the amount of interest. Okay. What can go wrong in this? This is multiplying three variables together. Very simple. We expect you know how to do that. The only thing that can go wrong is messing up the units. So I would keep your eye squarely placed on the units. Here is an example of watch out for the units. So for example, the rate of interest is often written as per year, but then the amount of time is not written per year. So you might have an issue. You need to make sure that you're either keeping track of the units sort of on paper, or that you use the same unit everywhere. So we'll do an example here. Let's do example 162, part 2. They have the rate is 5.25% PA, and the time is 243 days. And a little secret is that PA means per year. So this means per year. Per year. So the rate is 5.25% per year, which you could rewrite as 0.0525. A percent is 1 over 100. And then you could keep it as 1 divided by years, right? A per year means you have 1 per year. So I would leave it like that. Some people also like to just leave it as 0.0525, and then they remember, so they have to mentally remember, always use years. Always use years. So you can do either of those. You can make sure to leave the years in so you don't have to remind yourself, it's written down for you, or you can remember it. If you do time, time is 243 days. 243 days. That is from this part of the question. And to convert days to years, I'm going to use the method that I introduced when we did radians to degrees, is I'm going to take 243 days, and I'm going to multiply it by something that I know is 1. What do I know is 1? I know that 365 days is the same as 1 year. So 365 days divided by 1 year is 1. So I'm going to multiply 365 days divided by 1 year. I know that this is 1. So I'm going to multiply by this. This is equal to 1. So by multiplying by something that I know is equal to 1, I haven't changed the equation. The equation is still perfectly true. And now it will hopefully be in years. And what's going to happen is the years, the units, will cancel out from the numerator and the denominator. So what's going to happen is I'm going to look at days over here. That's the days in the numerator. And it's going to cancel out with the days in the denominator. So when I go to circle, this is a problem. I wanted the days to cancel out with the numerator and the denominator, but I have days in the numerator in the top, and I have years in the denominator. So they don't match. So something is wrong. I've made a big mistake. And in fact, if you type this on your calculator, you would get 243 times 365, right? And 243 days is not some huge number of years. It's not like 10,000 years. It's got to be like less than a year. So for sure I made a mistake. The thing I did is I put it upside down, and this little canceling out made sure that I realized that I did it wrong. So let's fix it. Let's fix it. Let's do 1 year divided by 365 days. And now it is still equal to 1, right? But it's upside down. And now everything will work perfectly fine. The days will cancel from the top and the bottom. And so I'm going to be left with, on a calculator, 243 divided by 365. And it's the units are years, right? The days cancel. What's left over is years. And there you go. OK. And now I have something in units of 1 over years. I have something in units of years. When I go to multiply r times t, the years and the 1 over years are going to cancel. I'm going to get something that has no units. So r and t were made to be multiplied together to get a nice number. So some people will go one step further, and they will do what I said. They'll just say 243 divided by 365. And then they have to remember that it's in years. I like to leave the units in so I can make sure that I'm not messing things up. So there you go. That was an example of getting the units right. I'm going to move on to this question of really doing one. I'm going to do part 3, but this is a good place to stop if there's any questions or comments about the unit change. So that's one thing you'll have to do in life. Probably the most useful lesson of the whole course is how to change units. So you'll use it even when you're like, building a chair for your son or whatever. You'll need to know units. So let's do this example. We want to calculate the simple interest. The formula is interest is the principal times the rate times the time. If you write 1923.60 times 3 times 215, then you go straight to jail. Even though the numbers are 3, 215, 1923.60, you forgot about the units, you're going to get the completely wrong answer. So don't do that. Write it with units. What are the units here? This is in dollars. 3 is actually 3% per year. So if you want, you can write it as 3% per year with the years on the bottom. And it's 215 days. So now it's perfectly correct. Before, without the units, you would actually get the wrong answer. You would type it into your calculator, you would get something wrong. 3% I can do, $1923.60. 3% is 0.03. Then I have 1 over years, and then I have 215 days. So I have days on the top and I have years on the bottom. To make those go away, to make it nice, I'm going to multiply by what I know is equal to 1. What do I know is equal to 1? It's, let's see, do I want days on the top or days on the bottom? Let's not make the same mistake I made before. Well, okay, I want the years on the top so that the years cancel out this year on the bottom, right? And then I want days on the bottom to cancel out these days. So it should be times 1 year per 365 days. So I've multiplied that thing in pink is equal to 1. It hasn't changed the formula, but it has corrected the units for me. Because now I have days both on the top and the bottom. There's a days here and a days there. Those cancel out. And I have a years here and a years there. So what is the final answer? It's something you can type in your calculator. 1923.60 times 0.03 times 215 times 1 over 365. And that will be the right final answer. I guess it's all in dollars. The units are dollars. Now you can put it in your calculator and you will get the right final answer, which if you do, you should get 33.99. 33.99. Okay. Questions or comments about this one? Yeah. Oh, do you have to use units? Yes, okay, so the units, this is interesting, the units are the same as the units for the principal. So whatever you are accumulating, if it's dollars or if it's euros or if it's yen, the interest will be the same units. And in fact, you could imagine a world where it's like kilograms of gold or whatever, and then it's kilograms of gold again. Yeah. Exactly, yes, yes. There's 3 examples, and I'll do the other 2. That's right, yeah. Yeah, it should be, yeah. I agree with you. As written, it's not so clear. This is 3 problems. Yeah, we only did 1. I'll make the other 2 extra if you want to see them as well. They get sort of harder and harder. I just jumped to the hardest one because I think it's the most instructive. The one with 1 year is actually quite easy because you have something per year and you have 1 year. So like, even if you don't know what you're doing, you'll still be able to do I. Yeah. Yeah, no, thanks. This is good to clarify. Okay, so that's basically all we're doing for simple interest. There's a few other things in the book. For simple interest, one of them is like, okay, you have this equation I equals PRT. You can solve for I. You could also rearrange and solve for P or R. I'm going to skip those for now, and I'll make this an extra video. There's this idea of the future value. I am not going to ask you guys about future value. So we're skipping future value. I do want to do a little bit on compound interest before we go. So we're jumping to compound interest, which is this idea of the interest on your interest. So far we've only talked about simple interest. It is a linear. Simple interest was linear. So simple interest. Simple interest was the formula I equals PRT. And I want to draw your attention to the fact that it is linear in t. It is something times t. If you double the amount of time, you double your money. That's simple interest. Compound interest is what I call superlinear. It's superlinear. It's superlinear. Why is it superlinear? If you double the amount of time you leave your money compounding, you will more than double your interest. So you're getting better than a linear rate. It's superlinear. And in fact, we're going to see it's actually exponential, and it ties into all these other things we've been doing in the course with exponentials. And so this is the idea, the addition of interest to the principal. Our principal amount, instead of being a constant p forever, our principal amount is actually going up. Okay, and what I want to get to is this derivation. This is the idea. We want to get to this formula explaining, the formula is all the way down here. We want to get to this formula and explain why it is true. So I'm going to start by setting us up. I'll leave this on the board so you guys can see what it is. And we're going to fill in this little derivation of a thing. And to make a little concrete example, what I'm going to do is I'm going to imagine that I put my money in the bank in January on day 0. And at the end of the year, on December 31st, I'm going to call that's 1 unit into the year. We're going to imagine there's some number of periods where we get interest. And for simplicity, I'm going to make m equals 3. So there's going to be this period from January to April. That is 1/3 of the way into the year. There's April to September. September is 2/3 of the way into the year. And then there's September to December. That is the last third of the year. So we start in January. We start with P dollars. This is our money in our bank account. Our money is P dollars. How much money do we have in April? So we've gained some interest from January to April. We've gained some money from January to April. How much money have we gained? That is what is going on here. So we started with P dollars, and we gained P times R times T, P times R times T in interest. But I can tell you what T is. T is 1/3. 1/3. 1/3. Why is it 1/3? Because we only did 1/3 of the year. In general, for my example, it's 1/3, and that was because m is a third. In general, it should be 1 over m. 1 over m. And this is the idea at the top of this box over here. The per period interest rate is r over m. So if in 1 year you get an interest rate of r, how much do you get in one little period over here of 1 over m? You get r times 1 over m. So this r times 1 over m you could think of as one single number, the per period interest rate. The important thing to notice is that you can factor p plus p times r over times 1, p times r times 1 over m. You can write p as p times 1, and then now you can factor out a p. It's p times 1 plus r over m. Okay, so in January to April, we started with P dollars, and then in April, after we got our interest, now we have P times 1 plus R over M. And here's the thing. All that work we did of calculating how much money we had in April given what we had in January, the same work applies from April to September. To go from April to September, we're going to do the same thing that we did to go from January to April. So January to April, we gained some money. April to September, we gained some money. How much money did we gain? We always multiply by 1 plus r over m. And why is it 1 plus r over m? It was that calculation and that factoring we just did. So in September, how much money will we have? It will be p times 1 plus r over m squared. Squared. It's p times 1 plus r over m squared. How much will we have in December? Again, you're going to multiply by 1 plus r over m, and you're going to get 1 plus r over m cubed. Let me do this in red. We're multiplying by 1 plus r over m every time, 1 plus r over m. And so you end up with p times 1 plus r over m cubed. So the general formula is, okay, after 2 pay periods, that's what we have in September, p times 1 plus r over m squared. And after m pay periods, you end up with this formula. So the final formula that we want to get to is this. So I'll go back and fill in those other things next time, but this is the formula that you get. If you do it m times t times, you get 1 plus r over m to the power mt. Okay, thank you for bearing with me while I finish that. I'll see you guys on Wednesday, and I'll be around here for questions if you have any.